All right, welcome to today's colloquium. It's my pleasure to welcome Shaz Qadeer from Microsoft Research. He is no stranger to us. He taught a grad course here on model checking a few years ago. He's collaborating with Louis Sezi. He works with Tayfun, who's joined on some of this work, who visited us for a year. Shaz has done a lot of work on analysis of concurrent programs, concurrent software. In fact, so much so that I'm now one of the few people in our research area that remember that he started out a hardware verification guy. And today he's going to tell us about his QED system. Okay. Shaz.
Thank you for that wonderful introduction. It's a pleasure to be here. I'm going to tell you about some joint work with three of my colleagues at Koç University in Turkey, Tayfun, Elmas, Ali Sezgin, and Serdar Tasiran. And this is about the QED system that we have developed over the last couple of years. It's a system that's targeted towards verification of concurrent programs. This is a problem that has acquired renewed urgency and interest in the last year or so, a couple of years, because it is widely perceived that we're going to have machines with multiple cores in them. The performance of a single CPU is not going to increase anymore, and to get more performance, people are going to have to write explicitly concurrent programs. So concurrency is notoriously hard to get right, and so it's increasingly important that we understand or try to understand how to build concurrent software in a reliable fashion. So I, in particular, am interested in the correctness problem related to concurrency. So the problem is, given a concurrent program, we want to make sure that the program behaves correctly for all inputs and for all interleavings. And we would like to do this, solve this problem in a scalable fashion. Scalability means that you want to be able to scale to large programs, and therefore we would like to be able to reason about programs by breaking them into pieces, trying to mimic how verification was done for sequential programs. So why do we want to do this kind of decomposition? Well, program verification, as we all know, is an undecidable problem. So what does that mean? The program verification problem is we have a property, we have a program P, and we have a specification of that program S, and we want to have a computer check that P satisfies S. Well, it can be done, right? So because it's an important problem, people have tried to circumvent this difficulty, right? And the way this difficulty has been circumvented fairly successfully is to put a man in the middle, or a woman. In this case, it's Shaz. So the idea being that the human being interacts with the computer to construct a proof of correctness of the program, and in the process, if the proof fails, then it finds bugs, right? So this is the idea. And for sequential programs, we have a well-developed theory of how the programmer should interact with the computer in the form of assertions. So we have this rich theory of assertions such as loop invariants and preconditions and postconditions and object invariants. And these kinds of assertions allow us to break the proof of a large program into pieces, each of which can hopefully then be discharged by the computer, right? And this is not, theoretical stuff. For example, proof technology based on assertions is widely used inside Microsoft to find things such as data race conditions and buffer overruns and things like that, right? So what we want to do is we want to be able to do something similar, do this kind of compositional reasoning based on assertions for concurrent programs, right? So let's look at perhaps the simplest concurrent program that one could write and see what are the difficulties that arise because of concurrency, okay? So this is a simple program in which there are two threads, A and B. And each thread is task is to increment atomically a shared variable x, okay? But the underlying, the substrate on which the program is going to run does not provide an atomic increment operation. Instead, it provides an atomic read and an atomic write. So how do we implement an atomic increment using those two primitives? Well, a classic solution is to use locks to protect accesses to shared variables. So these two threads are following a very simple protocol, locking protocol. Each thread, before it tries to access X, acquires the lock. Then it reads X into the shared variable, increments the shared variable into a local variable, increments the local variable, and then writes the value back into X. Okay. So now this program intuitively to us seems correct, right? And we would like to be able to prove that it's correct. And the proof condition is that if you start the program with X being set to some arbitrary constant C, then we would like to prove that once both the threads finish, both tasks finish, then X is equal to C plus 2. Okay? And pretty much this is what you have to do to prove this correct. So all proofs of concurrent systems in the worst case will end up being a proof of an inductive invariant. So you model the system as some kind of a state transition system, right? And then you provide an invariant which is preserved by every transition of the system, right? And it also ends up proving the property. So this is the invariant that you would have to write, okay? So this, I'm just trying to impress upon you the issue that this invariant is very complicated, even for a very simple looking program, okay? And of course, I mean, I'm sort of lying here. For this particular program, I'm sure you can find papers which can say that which will have this technique or that technique to solve this problem. But in general, this is a problem, that when you have concurrency and when you have interference between concurrently executing threads, the invariant becomes very complicated, and it's very hard to provide it. This is a very different story from what happens in the case of sequential programs, where for a property of comparable complexity, the invariants tend to be much simpler. Okay, so this is the first problem, the so-called invariant problem. The second problem is what I call the abstraction problem. Okay, so the way you scale formal reasoning is by building abstractions, whether, and this is true even when you're doing informal reasoning, right? So for that reason, you have the notion of abstract data types, you have the notion of modularity, encapsulation, and so on. So now, in sequential programs, again, the notion of abstraction is very simple, more or less. So if you had that piece of code on the left, which is again incrementing a variable x, if you wanted to abstract it, you could abstract it with the post condition that says that x is incremented. This piece of code increments x by 1. But if you have a piece of a larger concurrent program which is acquiring a lock and then incrementing x and then releasing the lock, it is not very clear what the right specification should be, right? Because you can't really use preconditions and postconditions because preconditions and postconditions sort of assume that the state at the beginning and at the end is stable. But we are writing preconditions and postconditions on shared state, which could be concurrently being modified by other threads. So what is the notion of abstraction in concurrent program? That's also not very clear. So what I'm going to try and do is convince you that QED provides some progress on both these fronts. It helps with both invariants and with abstractions. It's certainly by no means a complete solution, but it's a good step that will hopefully lead us in the right direction. Okay, so let's forget about that invariant-based proof of this program that we did earlier, right? Instead, let's try to mimic how we would intuitively reason about that program. Well, the way I, at least, would intuitively reason about it is I would say that, okay, each thread is acquiring a lock to protect some shared state and then releasing the lock at the end, right? So it's trying to implement a large atomic action from smaller atomic actions. The large atomic action being the atomic increment of x, and the smaller atomic actions being individual reads and writes of x, right? So what if we just try to simplify the program to capture this atomicity, right? And of course, the locking protocol is, has to be verified, because only if that locking protocol is satisfied will you know that this abstract atomic action is implemented correctly. But let's assume that that locking protocol is working correctly, or we can verify it separately. Then one transformation that we can do is to increase the grain of atomicity, right? Now, instead of having each action performed by a thread be a separate atomic action, we can wrap all the code executed by a thread inside a single atomic block, right? Does it make sense? So actually, you're welcome to ask questions in the middle of the talk. I like things interactive. So please stop me at any point in time if you have any questions, okay? All right, so now we have 2 threads, and each one is doing an atomic action. We have already done a huge amount of simplification, though you might not realize it. Why? Because in this program, if you wanted to write the invariant, all you have to do is write this much compared to all the crap you had to write earlier. And the reason is not that complicated. In this program, each thread has only 2 program counters because the stuff inside the atomic action is sort of hidden. You don't have to write invariants at those control locations. So even this is very good progress, but you can do even more. What you can do is you can say that, okay, each one of these actions is just an atomic increment, right? X gets x plus 1. Now you're doing 2 x gets x plus 1 in parallel, right? It doesn't matter in which order you do them because they commute with each other. So what you can do is you can eliminate the parallel composition and replace it with a sequential composition, right? And now you can verify this completely trivially using sequential methods, right? You don't have to write any invariants if you just provide this much to, say, a standard verifier, essentially a loop-free program, you're done. So this is the basic idea behind QED. Right? When you're faced with a hard problem, instead of trying to solve the hard problem, sidestep it. If the original program is hard, don't verify it. Instead, simplify the program. And once it has become simple enough, then you do your standard verification. Okay? So this is the QED mantra. Okay. And the way I'm going to set it, the formal system is going to be set up, although I'm not going to go into the details of the formal system, is that you basically maintain the program, and then you do transformations on it. And for us, a program is essentially the invariant of the program together with the program text. And then you start with the original invariant and program text, and then you keep changing it, strengthening the invariant or simplifying the program until the program is obviously correct. Or if it's not obviously correct, then it can be proved using sequential methods or methods that are understood better. And this solves both problems that I alluded to earlier. It solves the invariant problem because what you do is you don't write invariants on the original program. You write invariants on the program once it has been simplified enough, right? Like how we simplified the atomic increment example that I showed you earlier. It also solves the abstraction problem because implicit in the QED story is the idea that the abstraction of a concurrent program is another concurrent program. As you go from left to right, modifying the program, each successive step creates a new abstraction. So it's just that we have an original concurrent program, and then you keep simplifying it. Each step, you have a simpler concurrent program, which is a specification of the previous one. So instead of preconditions and postconditions, you use programs as specifications.
And you're going to show us the equivalence of those?
Right. So I'm not going to define it formally, but it'll be clear. So the idea is that as you go from left to right, the hope is that if at the end you verify the final program, then you have verified the original program. So what you have to do is make sure that all behaviors, at least all seemingly erroneous behaviors of the original program are preserved in the final program. And that is going to be guaranteed by all the transformations that I'll suggest. Okay? Okay, and then I gave you one example, which is basically a very simple lock-based atomic increment example. But the QED idea is a very general idea. It's not the case that it works only for these simple log-based examples. In fact, consider this example, the atomic snapshot example. This is a lock-free algorithm. So let me take this is also another one of the running examples that I'm going to use throughout the talk. So let's spend a few minutes trying to understand this example, because I'm going to revisit it. Okay? So in this program, what we want to do is we want to implement 2 atomic methods without acquiring any locks. One method is, so what we have is an array of integers, okay? And I have a write method, which takes an index into the array and can write some value into the integer at that index. I also have a snapshot method, which can take 2 different indices and then provides an atomic snapshot of the integers contained at those 2 different indices, right? Now, all I have, the primitive that the underlying system provides to me is read and write of an individual integer. It does not provide me with an atomic read of 2 integers, right? So that is the challenge that is being solved by this program. Given an atomic operation that reads and writes one individual integer, how do you construct an atomic operation that can read, that can take an atomic snapshot of two integers? Okay? Yeah?
Aren't you just pushing your proof down in that by assuming that things in the atomic bracket are sequential? That you can't do a parallel run?
Exactly. So you're absolutely right. When you have an atomic action, then inside it, once an atomic action is executing, there is no interference from somebody else. It executes in isolation. So it depends on it depends on how much work you do inside that atomic. So what happens is that the challenge always is going to be the following. The primitives are going to let you do only a little bit of work inside an atomic. So they'll say, okay, I'll let you read a 32-bit value, right? But using those primitives, you have to conceptually construct large atomic actions, which might end up reading multiple 32-bit values, for example, in an atomic. So the challenge of concurrency is to somehow eliminate this sort of ostensible interference and get larger atomic actions from smaller atomic actions. That's what all these programs try to do, okay? And that's what we want to verify, that that's being done correctly. Does it make sense?
It kind of makes sense. It still seems to me to bypass the problem of how the atomic verb is in fact implemented within the system.
So I am deliberately bypassing it because I'm actually trying to do static reasoning about it. It is not interesting from the point of view of this talk about how that atomic is implemented. Somehow it's being implemented. Given that, I'm trying to reason about it. Okay? So for example, here in the implementation of snapshot is using this atomic keyword here, right? But inside that atomic, I'm assuming that there is some code being executed. This is just a modeling thing. I'm not worried about how this atomic is going to be implemented. Okay? Okay, so I was trying to explain how this code actually implements this kind of atomic snapshot. And the way it implements is by introducing version numbers. So corresponding to each integer in the array, you store not only the data value, but also a version number. And now every write operation atomically increments, atomically updates the data value and also increments the version number. Let's assume that that the data value is 16 bits and the version number is also 16 bits, so it fits within a 32-bit quantity. Okay? And now what does the snapshot do? Well, the snapshot actually is brilliantly simple. So what it's doing is it's reading the two addresses one by one. It reads them twice. So these two lines read them the version numbers into the local variables VA and VB, and the data values into DA and DB. And then you just compare the version numbers again. And if the version numbers got incremented in the meantime, you return failure. So the variable S, which is an output variable of snapshot, tells you whether the snapshot succeeded or not. So it's basically you read once both the values, then you read them again, and then you compare them. If the version numbers are the same, you return success, and then you have the actual snapshot in the variables DA and DB. Otherwise, you return failure. So this snapshot can always fail, in which case the client is supposed to try again. Okay, any questions about the snapshot? It's very important we understand the snapshot algorithm because I'm going to come back to it, okay? All right. Ask me later if you want. Okay, so now the most important thing to notice about this example is that there are no locks being acquired, right? Yet, somehow these atomic snapshots are being constructed. And what I'll show you is that QED has the power to take the code on this slide and transform it into the code on this slide, right? So in this slide, notice that I have look at the body of snapshot. You have an atomic around both the updates to both the reads of ma.d and mb.d, and the indices a and b. So there are two things going on. First of all, the code has become non-deterministic. So why is it non-deterministic? Because I am using this have a keyword. So have a, followed by a list of variables, it means that you take those variables and put arbitrary type correct values in them. It's a non-deterministic thing because it always allows the snapshot to fail. But if it succeeds, then you get the power of magically, by magic, reading both ma.d and mb.d into dA and dB respectively. Okay? So I'm going to show you later how to convert this lower level snapshot into this high level snapshot using simply QED transformations, very simple things. Okay. All right. So a little bit, I showed you a few programs that I wrote, but I'm going to show you a little bit more. But before we get into the examples, I just wanted to make sure that there's no confusion about the programming language that I'm using and how you model, synchronization using my programming language. So this is the syntax of my programming language. You have things like assume E, assert E. So assert E is simply an assertion, right? Assume E is like a blocking thing. So a thread that executes assume E blocks if E is false, and then another thread can execute, right? Havoc X I've already explained. We have assignment, we have if then else, we have loops. I'm going to be using procedure calls with explicit out parameters. This is parallel composition, so you can execute two statements in parallel. And then finally, we have this thing called atomic. So this atomic is going to serve a dual purpose. It's going to be used to model synchronization, as I'll explain in the next slide. And it's also going to be used in our transformation. So remember that we took small atomics and we created large atomics out of them. So it's going to result, so in the intermediate programs that QED generates when it's doing its transformations, they're going to use atomic spanning over large code blocks. And the semantics is very simple. You have a collection of threads. So each thread has its code, and then there's some shared store. And in each step, one thread is picked non-deterministically, and it executes one step. Okay? And if that step fails an assertion, then that thread basically gets stuck in some wrong state, right? And that means that the entire program has gone wrong. If a thread fails an assume, that means this thread is blocked in this state, but other threads can proceed, and then you pick another thread, it executes, and then you can try this thread again. This is the idea. Yes?
So can atomicity be inferred, or does that be specified by the programmer? Based on like data access or some other metric?
So think of atomic here as a way to construct programs. So imagine that there is some system by magic that is going to implement the semantics of a program that uses atomic. So how that implementation is going to be done is a separate issue, because we're not. I mean, this talk is about verification and modeling, as opposed to how to build a runtime system that is going to implement those atomic operations. Okay. Good. So let's take a few examples. Oh yes.
Back up. Does the assume spin on the predicate being true, or does it?
Yeah, so you can imagine that it tries to evaluate that, and if it is false, then it just sits there, not doing anything.
Okay, so then someone else gets to turn it.
Exactly.
It's still false. It just passes.
Right.
Okay.
Yeah, Dan.
I wanted to not let people get too concerned about this atomic thing. We can imagine that the source program is written in terms of locks, which you would then encode as a little atomic that would spin on a Boolean variable.
You could do that too. So let's do a few examples. Let's write a few programs using these primitives. Maybe things will become a little clearer. Okay. So the first example that I want to show you is a semaphore. Okay. And so there are two procedures, up and down, and we are modeling the state of the semaphore using an integer variable count. And we have an atomic that atomically increments. For up, we atomically increment count. And for down, we have an assume followed by a decrement, right? Because a down is a blocking operation. It blocks until the value of count is greater than 0, and then you atomically decrement it. Does that make sense? So you can imagine that, like a thread is going to sit there waiting, and at some magical moment, it will suddenly discover that count is greater than 0 and just decrement it. Okay? All right. Let's take a look at lock. So a lock has two operations, acquire and release. We're modeling the state of the lock using an integer variable called owner. Okay? So the idea is that if no thread is holding the lock, then owner is 0. And then if a thread is holding the lock, then its ID, which is supposed to be an integer, non-zero integer, positive integer, it's stored in the value owner. So how is acquire going to look? Well, there's an atomic state, code block which blocks until owner is 0 and then sets owner to tid. So I'm going to assume that this tid is a special variable that keeps in it the ID of the thread that's executing the code. Okay? So imagine that the scheduler of the system sets it whenever a thread gets switched out. Right? And what does the release do? Well, a release also has an atomic. Inside it, there's an assertion followed by owner gets 0. So why do we have an assertion here? Well, this is trying to enforce the protocol that a lock is released only by the thread that previously acquired it. So you assert that owner is equal to tid and then set owner to 0. Okay. Here's another simple example. So example of a data parallel computation. We're trying to compute the sum of all nodes of the data value stored in all the nodes in a tree. And this example shows you how to use the structured parallel construct. Okay, so now let's take a, so any questions about, all this atomic, assume, assert, and all this business? Roughly clear? Okay, good. Okay, so now let's look at QED transformations. So like I said before, we have an invariant and the program text. And in each step, we're going to change either the invariant or the program text. Okay? So there's only 3 kinds of operations. That's it. Everything is going to be done using just 3 kinds of operations. You either strengthen the invariant. Okay? So do people understand what I mean by invariant? Invariant is simply a constraint over the set of global variables, which is inductive across each atomic action in the program. Being inductive, what does that mean? That if you start from a state in the invariant, and then you execute an action in the program, any atomic action in the program without interruption, then either the action goes wrong, or the state that it ends up in satisfies the invariant also. Okay, that's what I mean by an inductive invariant. Okay, so either you're going to strengthen the invariant, or you're going to do one of these 2 operations, reduce program or abstract program, and that's what I'm going to explain now. Okay, so this one I've already covered. You strengthen the invariant. You leave the program text unchanged, and then you strengthen the invariant. Okay, so what is reduce program? So reduce program is simply about playing with atomic. So what you do is you take small atomics and you create larger atomics out of it. Okay? And of course, this has to be justified, because whenever you take small atomics and you create a larger atomic out of it, you are potentially prohibiting some behaviors of the program. So there has to be an argument why that does not reduce the set of behaviors. Okay? And I'm going to show you how to make those arguments formally and check them using standard tools. Okay, so let's go down the list here. So the original program is shown on the left here, and the transformed program is shown on the right here. So the first 3 things are easy, right? They were atomic to begin with. So you just slap an atomic around it, no problem. Okay? Now, this one is a tricky one, atomic S1 semicolon atomic S2. You convert that into atomic S1 semicolon S2. You could potentially have removed behaviors. So we have to, this is not going to be justified in all situations. So we have to argue when is this justified. So before going down the rest of the table, let me first try to justify that. So in 1975, Richard Lipton wrote a paper that defined the idea of right movers and left movers. So a right mover is essentially an action performed by a thread that commutes to the right meaning forward in time, compared to any action in the program being executed by a different thread. Okay? So the idea is something like this. So imagine that there are 2 threads, a green thread and a red thread, right? So, and let's say that the green thread is executing the operation acquire, the atomic operation acquire, which is shown on the left here, right? And Y is some arbitrary action being performed by the red thread. What we want to argue is that no matter what the state S1 is, from which acquire starts followed by Y, the final state S3 can be mimicked by first executing Y and then executing acquire. Okay? So if that is the case, no matter what Y is, then you say that acquire is a right mover. So now I want to argue, for example, that acquire is a right mover, right? So what are the possibilities for y? Well, there are two possibilities. Either it's an acquire or a release, or it's some action that's got nothing to do with the acquiring or releasing a lock, right? So if it's an action that doesn't even touch the variable owner, then clearly the two will commute, right? Now let's consider the other case. Supposing that y is also an acquire. Is that possible? Can that happen, that y be an acquire? Somebody answer me. You were shaking your head. Can you tell me why?
Because if we acquire the resource once and we acquire it twice, then something bad can happen. So we can't have two owners.
Well, I mean, maybe that's another way of saying that the second acquire is going to block because it has an assume owner is equal to 0 here at the beginning, right? So the first acquire sets owner to TID, which is a non-zero value. So the second acquire after that is going to get blocked. So this execution is not even feasible, okay? Now, what about if y is a release? So in that case, what's going to happen is that, so can you tell me what is the end result of doing of the green thread doing acquire followed by the red thread doing release? What is the end result? What is the state S3 going to be? Paul?
The release will do nothing because the owner is not the green thread, which is the one that was acquired.
So no, so release is actually going to fail the assertion.
So it fails. Oh, it's an assert.
It's an assert, right? It's going to fail.
Yeah.
Okay? So now when you do it in the other order, we have to make sure that it still fails. But it is going to fail. Why will it fail? Because for acquire to have succeeded in S1, the value of owner must have been 0. And therefore, owner will not be equal to thread ID, which is non-zero. So release is going to fail even if you do it the other way. So now we have covered all cases. Make sense? Yes?
They fail in different stages, is that okay?
Pardon?
They fail in different stages, is that okay?
Yeah, that's okay, because this going wrong business has a special status. It trumps everything else. So you can always allow things to go more wrong. It will not affect, like the soundness of the transformation. That's why. Okay. Okay, so, yes?
Doesn't it fail in one case and block in the other, or am I misunderstanding?
No, it actually fails in both cases. So if you have acquire followed by release by a different thread, it will fail in both cases, whether you do the release afterward or you do it before. So it's fine. Okay? Okay, so now the other interesting thing is that there's an analogous notion to a right mover, which is the left mover, which is an operation that commutes to the left of any operation being performed by a different thread. So a release, you can actually show by similar reasoning that it's a left mover. Okay? I'm not going to go into the details of that reasoning here. But you have to do all this you have to do this case analysis. Okay? So then what Lipton showed is this reduction theorem, which I'm stating informally on this slide. The idea is that if you have a sequence of right movers followed by some action, at most one action, followed by a sequence of left movers, then you can consider them atomic. And the argument is roughly captured in this picture here. So the idea is that if you have a bunch of right movers, you can always commute them to the right all the way until you hit the operation in the middle. If you have a bunch of left movers on the right side, you can commute them to the left until they all sit together, and therefore you can put atomic. So the idea is that no matter what execution happens, you can always do this commuting without changing the final state, and therefore it's legal to put atomic around the entire code block. So in particular, if you have a right mover, then you can always smush it with the next operation, a single next operation. If you have a left mover, you can always smush it with the preceding operation. So that is the justification for this transformation. So to do this transformation, you have to show that either atomic S1 is a right mover or atomic S2 is a left mover. Okay? This one is again straightforward because assuming that what you access in the conditional is completely local. Okay? Now this one, while E do atomic S, the justification for this is very similar. It's a little bit more complicated, but it's also based on this idea of right movers and left movers. And for this one, where you replace a parallel composition of atomic actions with a sequential composition, again, you have to argue about commutativity. Okay? All right. So any questions about all this business here? This right mover, left mover business? Okay. So let me ask you this question. Supposing you have a counter x, okay? And the only operations in the program are atomic increments on the counter, okay? So when a thread performs an atomic increment, is that a right mover or a left mover?
Yes. It's and.
It's what?
And in your diagram.
It's both. It's both a right mover and a left mover, right? N is some arbitrary operation. We don't say what it is. Does it make sense? Okay. What we have done so far is we have looked at two of the transformations, strengthening the invariant and reducing the program. And now we want to look at the third transformation, which is abstracting a program. So what is abstraction? Abstraction is very simple, most trivial thing possible. So you have an atomic S. You take atomic S, you replace it with atomic S prime, as long as every behavior allowed by S is also allowed by S prime. There's no concurrency involved here because we're talking just about atomic actions, right? So for example, let's say that S is X gets 0, right? Then S prime could be X gets either 0 or 1, right? Because any behavior on the left is allowed by any behavior by some behavior on the right. Or S prime could be havoc X, because that's going to put some random value into X, right? Okay. So the important thing to notice about QED transformation, and I'm going to demonstrate this using more examples, is that these rules are symbiotic. So for example, abstraction often enables reduction. So a concrete action, an action as stated in the original program might not be commuting with other actions. But if you relax it, if you abstract it, then it will start commuting, okay? At the same time, reduction enables abstraction. So when you have taken a whole bunch of action, then you put an atomic around it, now you have a large program that you can try to simplify. It's hard to simplify small actions, but if you have a large program, then you can simplify them, right? And then all this program simplification enables simpler invariants. So all these rules together are surprisingly powerful, as I'm hoping to convince you. Over the last couple of years, we have managed to verify, using just a combination of these simple rules, a whole bunch of tricky algorithms from the literature, including a whole bunch of non-blocking algorithms and some fine-grained locking examples. So I'm not going to go into these examples, proofs of these examples, but what I'm going to try and do is illustrate this interaction between abstraction and reduction and invariance using two examples. And they are going to, yes?
Well, just to be clear about what you're doing here, right? These are all algorithms that were worthy of publication in the last 10 or 15 years.
That's correct.
The papers had an algorithm and maybe an English argument of correctness.
That's correct.
And now you formally verified it.
Absolutely. So that's exactly right. So these algorithms are complicated enough that they warrant publications, right? Okay, so people write publications about them. And in these publications, you have English argument. What we have achieved using QED is a fairly simple, I mean, not maybe all that simple but completely mechanized proof. So everything is verified finally by a theorem prover and interaction with a human being, which the human being supplies these transformations, and then the soundness of each one of those transformations is verified by the machine, okay? And what is going on is that you keep simplifying the program until you see finally a program that is just very simple. It's obviously correct. Okay. So I'm going to show you two examples, a spin lock example, and then we'll go revisit the atomic snapshot example that I showed you earlier. So, we've already seen how you model a lock, right? But that lock model was using things like assume, right, which are not really implementable. And there's a bunch of questions from the audience about what does it mean to implement atomic and assume and all that stuff, right? So let's start with a real implementation of a lock and show that it satisfies that abstract model that I constructed. Okay? So what does a real implementation look like? So this is a real implementation. So this is a CAS-based implementation. How many people know what CAS is? A few people don't. Okay, so CAS is an operation that is provided by some machines. It takes 3 arguments. It takes a variable address, and it takes 2 values. And what it's doing is atomically comparing the current value in the variable with the second value. And if they're the same, then it writes the third value into the address, into the variable. Okay? So it's comparing, so this particular cas operation invocation is comparing held to false, and if held is equal to false, then it puts true into held. Okay? And all that is happening atomically. Huh? It's all happening atomically. The hardware guarantees it. Yep. Okay, and what I want to do is I want to show that by using QED transformations that this program can eventually be transformed into that program, right? So none of all this cas, but it's a very abstract model. Okay, how do I do that? Okay, so notice that there are 2 main differences between the program on the left and the program on the right. One is that the data representation is different. The program on the left is defined in terms of a Boolean held variable. The program on the right is defined in terms of an integer owner variable, right? Which has strictly more information. It has not only information about whether the lock is held or not, it also has information about which thread holds the lock. That's difference number 1. The second difference is that the program on the right has large atomic actions. In fact, both acquire and release have one single atomic action each, right? Whereas the program on the left, the release procedure has a single atomic action, no problem with that. But the acquire implementation is fairly complicated. In fact, it has a loop. There could be an unbounded number of atomic actions during some invocation of acquire. So we have to resolve these 2 differences between this program. I'm going to do that step by step. Okay? All right. So the first thing I'm going to do is I'm going to instrument the original program with the new variable owner, right? So owner is keeping track of, first of all, what thread is holding the lock. So what I can do is I know that when the cas succeeds in acquire, then I know that the thread that was executing acquire has managed to grab the lock. So what I can do is I can just put a new a statement there which sets owner to TID. Okay? So this is completely non-invasive because I'm instrumenting the original program. I'm not reducing, I'm not doing anything unsound. I'm not changing, reducing a set of behaviors. Similarly, in release, what I can do is just I can make my atomic action a little bit bigger, and I can put my instrumented state in there. So I can assert that owner is TID, and I set owner to 0. Again, there's no problem because I'm only adding more erroneous, potentially erroneous behaviors, right? I'm not reducing the set of behaviors. Okay? So this is the first thing I'm going to do. Now I'm going to play a trick. I'm going to take that while loop, and I'm going to do surgery on it. I'm going to hoist out the last iteration of the body of that while loop, the iteration that actually breaks out of the loop. Okay? How do I do that? Well, I construct a non-deterministic loop, which is given by while star. So this loop non-deterministically spins with unsuccessful cases. And an unsuccessful cas is essentially modeled by this assume statement. Because it's saying that the lock is held. Right? Wherever it is held, it's going to just spin. It's waiting for held to become equal to false. And then at some non-deterministic point, it exits. And then that's the point it executes the successful cas. And the successful cas is simply modeled by an atomic statement, which is held is false, and then held gets true. So, so people believe that I have not really reduced the behaviors, the set of behaviors of this program, right? I'm just doing some, fairly syntactic surgery on the program. Okay, now what? Now what I'm going to do is I'm going to basically, the unsuccessful iterations of the cas loop don't really matter, right? So I might as well just relax that action, the action which says held not equal to false, with true, right? It's not doing anything. So now we have while star assume true. So this is just saying that you're just skipping. You just do a whole bunch of skips, right? So that can be summarized by a single skip, right? It's a completely local computation that is happening. You're sitting there doing nothing, okay? So you can think of it as a commuting operation if you want. So the entire loop becomes one skip. And so you can just eliminate it. So now we are at this point, okay? So we have made a huge amount of progress. We have eliminated the loop, but still acquire has 2 atomic actions in it, right? So what I want to do is I want to somehow smush these two actions together. And I'm going to do that by showing that this owner gets did, this action is actually a left mover. Right now it's not a left mover, because imagine if you have two operations by two different threads, each executing owner gets did. So let's say the thread IDs are 1 and 2. The order in which you do owner gets 1 and owner gets 2 affects the final value of owner, right? In one case it will be 1, in the other case it will be 2. So this is not a commuting operation right now. But what I can do is I can change the operation. I can abstract it. And in this case, I'm going to abstract it by adding an assertion to it. I'm always free to add assertions. Adding assertions is a kind of abstraction, okay? Because you only introduce possibly wrong-going behaviors, right? So here, what I'm doing is I'm adding this assertion to capture the intuition that by the time the CAS has succeeded, it must be the case that owner is 0, that nobody holds the lock. And I'm now, I can now go ahead and set owner to TID to acquire the lock. So I put that assert there. And now by the nice thing is that by putting that assert there, now this atomic action assert owner equals 0 followed by owner gets TID, it becomes a left mover. It starts commuting with itself. Because what's going to happen is that if you have one thread executing assert owner is equal to 0 followed by owner gets TID, followed by another one of them is going to go wrong, right? Doesn't matter which order you do them, okay? So turns out that this is a left mover, and now you can smash those two actions into a single atomic action, okay? Now we are very close, right? All we have to do is convert this assert into an assume, and then we are home free, right? We have to verify this assertion, right? But how do we verify this assertion? Well, now we can introduce an invariant. So what is the invariant of this program now? The invariant is that owner, the variable owner is 0 if and only if the variable held is false, right? Because both are saying, both conditions, owner is 0 and held is equal to false, saying that the lock is not held, right? So when we add this invariant, we have to verify that the invariant is inductive. As you can see, both these atomic actions preserve the invariant, right? So this atomic action sets owner to TID but held to true. So both sides of the if and only if become false. This one sets owner to 0 and held to false. So again, both sides of the if and only if become true. Okay? Now once you do this, you can use that invariant to discharge this assertion, right? Why is that? Well, if the invariant holds at the beginning of this atomic action and held is equal to false at the beginning of it, right? That means owner must have been equal to 0 at the beginning from this invariant. And so what you can do is you have now managed, using that invariant, you have managed to convert that assert into an assume. Now all we have to do is we just hide the variable held, and now we have a program that's only in terms of the owner variable. Okay? That makes sense? Okay. So now it is very important to note when an interesting point about this invariant. This invariant that I wrote down, note that this is an invariant on this program, a program in which both acquire and release have single atomic actions. However, it is not an invariant on this program. Why is that? Because in this program, there are two atomic actions. One atomic action is setting held to true, and the other one is setting owner to TID. So after the first one has executed, but before the second one has executed, the invariant does not hold, right? So to write an invariant for this program, you'll have to do more case splits and so on. So this is very important because what we have observed is that by suitably increasing the grain of atomicity in the program, by having larger atomic actions, we manage to simplify the invariant. So for this program, the invariant is very trivial. But this thing on larger programs becomes extremely important. Okay? That's why it's very important to write invariants only once you have large atomic actions. Okay? All right. So what I wanted to do was, maybe you guys, the reason I wanted to bring this up, other applications of QED, is that not everybody is as gung-ho about program verification as I am, right? So, but still, it might be the case that these ideas might be useful to you in your work, right? So there are a couple more, areas of research which might benefit from QED-like ideas. So one of them is concurrency testing and verification. Why do I distinguish between what I have been describing, which is also verification of some sort, with concurrency testing and verification? Because concurrency testing and verification is, some idea of, lightweight analysis and testing, right? You're not trying to do, fully modular, compositional, fully sound proofs as we are trying to do in QED. You want to do some amount of testing, you want to do some amount of static analysis, and you want the analysis to scale to large programs. What can QED offer in that situation? The other thing is that this area of programmer-assisted parallelization. So you have programs, possibly legacy programs, which are sequential, and you want them to run faster on these multi-cores, right? Now, there are all these compilers, which together with some programmer annotations, try to construct parallel programs with hopefully the same semantics as the original sequential program. What is the justification that those compilers are actually doing the right job, that they're actually preserving the semantics of the original sequential program? So I think what QED does, which is trying to bridge this gap between sequential programs or non-deterministic sequential programs and parallel programs, can be helpful in that endeavor. So let's take a look at concurrency testing and verification. So here the main challenge from the point of view of doing precise verification, right, relatively fewer false alarms, is that you hit this combinatorial explosion in the number of interleavings that you have to consider to verify the program. And this combinatorial explosion depends on the number of threads in the program and the number of scheduling points, right? So what QED can help you with is to eliminate, in a sound way, scheduling points. So for example, if you can detect or conclude that some action in the program is a right mover, then you can eliminate the scheduling point right after that action, right? Or if you can show that some action is a left mover, then you can soundly eliminate the scheduling point just before it, right? So for example, if you can show that your program is data race free, then you don't have to insert scheduling points at read and write accesses to data variables, right? On the other hand, you might be using QED-like techniques, you might be able to use abstraction on synchronization variables to infer that they are right and left movers, and therefore you can eliminate. So just to give you an example, imagine that you were using spin locks in your program, but your spin locks had one extra operation. There was a try-acquire operation also in addition to acquire and release. Now acquire is no longer a right mover, right? Because if you have an acquire followed by a try-acquire, then an acquire will succeed, that the try-acquire will fail. But if you did it in the other order, then the try-acquire will succeed, right? So in this case, what you can do is you can you can relax the semantics of try-acquire and let it fail arbitrarily in non-deterministic fashion. And then as soon as you do that, you can again convert try-acquire and acquire into right movers and release into left movers. So even if you had a try-acquire in your spin lock library, you can still reason with right movers and left movers by using an appropriate abstraction. Similarly, with programmer-assisted parallelization, we have now realized that effective parallelization requires abstractions. So the idea is that if you take the original sequential program, you will not be able to parallelize it because of these apparent dependencies. So what people have figured out is that what you want to do is you want to take the original deterministic sequential program and you want to relax its semantics to include more non-deterministic behaviors. And then you let your parallelization pick one of those behaviors. So again, you can justify this using QED. And then, so I'm trying to do some work in that direction. Okay, so that's the end of the talk. Questions?
Okay, sort of back to the question, these transformations, I mean, how hard is it to get them right in practice? I mean, you've done a bunch of these. I mean, are there just classic mistakes you make, and how do you find out when you've made a mistake and things along those lines?
Right. So my hunch is that so these transformations are very related to what is loosely termed the concurrency control mechanism. So my feeling is that, so they are sort of like a formalization of what is known as a concurrency control mechanism. So my hunch is that there's going to be some bounded number of these concurrency control mechanisms, and they are going to appear in different guises in different programs. So the point being that there's a, I think that there's a bounded number of patterns, but those patterns have to get instantiated based on, this program or that program, because that program has a different data structures, but the principle is the same. So capturing all those patterns is challenging. I mean, you have to sort of, formalizing those patterns is hard, but I think that there's a bounded number of them. But the tools that we have, if you make a mistake, they will find them for you. So there's this interaction. Then you have to go and fix it. Yeah.
Let's thank Shaz again.